Greetings everyone. I am Manya Chattopadhyay, and me and my team has developed a vehicle safety system by detection of speed breakers and potholes on road and communication through of that detected speed breaker or potholes. So I'd like to present my team: Alan, me, myself, Mainak, Sudarshan, Christian, Noel, and Pratik. We have built this system. I'd like to give an overview of why this system is needed, the statistics of the accidents that happen in India because of speed breakers and potholes. As you can see, this is a newspaper cutting from Indian Express. So you can see the values and statistics that happen because of the speed breakers. Here's another statistics which reflects the uh, deaths and the road accidents because of potholes. Here's a concept visualization that the camera will be placed in front of the car on the dashboard and will detect the potholes and the speed breakers. This is one of the schematic representations that a car will have a camera, Raspberry Pi, and a LoRa, and it will detect the speed breakers and communicate to the cars in a particular radius. As you can see, there are four checkpoints in the project: identification of compatible hardware, designing of ML model for the task, choosing a platform for running that trained ML model, and integration of ML model with the hardware. So we have used the Raspberry Pi 4 64-bit Bookworm microprocessor and microcontroller for this project. We have used a HDMI cable, 32 GB flash SD card for basically like loading the OS and running it on the Raspberry Pi, and also the Raspberry Pi power cable, the entire development kit we have used for the Raspberry Pi 4 64-bit Bookworm. Now comes the overall block diagram. So as you can see in the block diagram, we have the Raspberry Pi 4, and it has a display unit and peripheral input devices like a keyboard and mouse, and it also has a USB webcam which takes in live video and predicts it. So we already have a computer vision model trained. So as you can see here, we have the computer vision model trained. So the USB camera captures the live frame, sends it to the model, which predicts whether it is a pothole, speed breaker, or an obstruction. It sends the prediction to the display unit with the help of a bounding box on the frame itself, and then it is communicated to the driver that whether a pothole or a speed breaker is present or not. Now, coming to the dataset used, we didn't have a publicly available dataset with lots of images of speed breakers, potholes, and obstructions along with the labels. So what we did, we collected various types of images of speed breakers and potholes, around 100 images. Also considering the Indian road conditions as well, we took pictures of Indian roads as well, and we labeled it using an annotation tool called Label-IMG. It's a Python-based tool which helps us to generate an XML file with the labels of each and every image, which we draw actually boxes around the target area of prediction, and it gives us an XML file for basically training our model. So you can have the link to the image dataset out here, and if you want the image dataset along with the labels, you have the link here. Now comes the visual representation of how the label IMD software looks. So this is the label IMD software where you draw a bounding box around the area of interest, and I had three classes: potholes, speed breakers, and obstruction. So the model predicts into these three classes. So now we have used efficient at light, which will be explained later in the video with Sudarshan. And moving on to the next part, you can see the model parameters like the input. It is a TensorFlow Lite model actually. So TensorFlow Lite, it's a very lightweight TensorFlow framework for running the model on the board itself. So one of the points that we highlighted is like we are not using any kind of cloud or any other third-party softwares for running our model. We are running it on the board itself. So it makes it very much robust and real-time as well without any latency or other like the overhead in the communication. So we are reducing that and we are eliminating that almost. So it's almost real time because it's running on the board itself. So these are the two parts: model properties and the inputs. You can see out here that what are the dimensions and what are the properties of the model. Now next comes how do we train the model. So you have find the Google Colab code. We have also the saved model as well, like best.tflite. You also have the detect.py, and you also have the train.py. Each one of them will be explained by the respective team members in the later part of the video. So this is the output that we have received. So as you can see, this is the that is it. So we didn't have actual speed breaker, so we just showed it on the phone screen and it's detecting as a speed breaker as of now. So this is the first output. Now second is the pothole detection. So this can also detect multiple potholes. For example, it's an Indian road where multiple potholes are getting detected, as you can see out here. So this is we're also showing this through a phone by the help of a webcam. And this is the third output where he's one of our teammate. So he's detected as an obstruction. So a human or any other person would be shown as an obstruction out here. So yeah, so this is the about the output of the model, that how it is detecting and what it is detecting. And the challenges faced during the project was non-availability of dataset. We didn't have any dataset. We had made our own bugs in the Label IMG software. So Label IMG is a software that is already pre-built by Python developers, but there was some bugs which caused the software to automatically close. So we removed that bug by including changing two files like canvas.py and labelmg.py. So the links for those files in the codes for those files are given in my GitHub repo, so you can view it out there. And also the choice of efficient, lightweight deep learning framework that can run on IoT devices. So our main motive was that the model should run on the device itself and not on any other platform to reduce the latency and everything. So we used TensorFlow Lite, which made use of a efficient net model, which is also a very light deep learning framework. So we had made this, and this is the link for the GitHub repo that we have built. So in the GitHub repo, everything is there, all the project files and everything. Also, I'd like to show two things. That as you can see, this miniconda.sh. So this is a micro environment. Miniconda is a miniature version of Anaconda, which is built for embedded systems and IoT devices only. So if you don't have a Raspberry Pi but you have a Linux system, so you can just copy this sh file in your Linux system and execute this sh file. It will create an exact simulation of the environment where this model was built. So this makes it in like board independent as well as environment independent. So you can run this sh file on any device, on any laptops, computers, supercomputers, anything, and you can create this exact same environment for running this model or creating this model or improving this model. So this makes this sh file makes it board independent. Also, we have converted this to a header file. We have converted the ML model to a header file and a CC file. So .h file and .cc files are used to run the models on Arduino boards. Like we have used Raspberry Pi, but if someone wants to use like this model in an Arduino board, so you can just download this file TFLITE model.h and then invoke this in the top of his header file, like in hash include TFLITE model.h, and you can start using the model, the predictions of the model by configuring other parameters. So I've also made it for the Arduino board as well. So these are the three things that extra we have done in the project to make it board independent, and also it can be used by all type of system users and configuration users. So the later part will be handled by my teammates, who will be explaining each and every part of the project in details.
The Raspberry Pi for Bookworm 64 bits is a variant of the Raspberry Pi for Single Board Computer (SBC), specifically designed to cater to educational and hobbyist interests, particularly in the realm of computing and programming. Let's delve into its technical details, advantages, and potential applications. Technical details. Processor. The Raspberry Pi 4 Bookworm 64 bits features a 64-bit quad-core ARM Cortex A72 processor, providing a significant performance boost compared to its predecessors. This processor architecture allows for efficient multitasking and enhanced overall performance. RAM. It typically comes with varying RAM configurations, ranging from 2 GB to 8 GB LPDDR4 RAM. The increased RAM capacity enables smoother multitasking and better performance in memory-intensive applications. Connectivity. The board offers comprehensive connectivity options, including Gigabit Ethernet for high-speed wired networking, dual-band 802.11 AC wireless networking, and Bluetooth 5.0 for wireless connectivity. Multiple USB ports, such as USB 2.0 and USB 3.0, for connecting peripherals, such as keyboards, mic, external storage devices, and more. Video output. It supports dual monitor configurations via two micro HDMI ports, each capable of outputting up to 4K resolution. This makes it suitable for multimedia applications and projects requiring high resolution displays. Expansion. The Raspberry Pi 4 Bookworm 64 bits retains the GPIO, General Purpose Input/Output header, allowing for easy interfacing with sensors, motors, and other electronic components. Additionally, it features a micro SD card slot for storage expansion and booting the operation system. Operating system compatibility. It is compatible with various operating systems, including Raspberry Pi OS, formerly known as Raspbian, Ubuntu, and a range of other Linux distributions. This versatility makes it suitable for a wide range of products and applications. Advantages. Affordability. As with other Raspberry Pi models, the Raspberry Pi for Bookworm 64 bits is highly affordable, making it accessible to a wide range of users, including students, educators, hobbyists, and DIY enthusiasts. Versatility. Its small form factor and extensive connectivity options make it suitable for a diverse array of projects, ranging from simple programming exercises to complex IoT stands for Internet of Things applications and multimedia centers. Education tool. The Raspberry Pi for Bookworm 64 bits is an excellent educational tool for teaching computer science, programming, and electronics, and other STEM stands for science, technology, engineering, and mathematics subjects. Its affordability, ease of use, and wide community support make it ideal for classroom settings and self-directed learning. Community support. The Raspberry Pi ecosystem boasts a vibrant community of users, developers, and enthusiasts who contribute to an extensive repository of projects, tutorials, and resources. This wealth of community support enhances the learning and project building experience for users of all skill levels. Thank you.
Good day to all. Now I'll be explaining the TF file custom model that comes with a project that detects the plot holes, obstructions, and other difficulties faced by drivers while driving. I'll be proceeding. Well, as you can see, at first, we are setting the Python path environment variable. It specifies a list of directories to search for Python modules and incorporating it. After this, we're downloading the Miniconda installer script from the specified URL. Miniconda is a lightweight version of Anaconda, a package manager and environment management system for Python. After installing it and executing the installer, we are even updating the Conda package. And going forward, please wait a second. Now we are importing the built-in Python module, sys, which provides an access to system-specific parameters and functions. We're instructing the Python to search for modules in this specified location. After this, we're creating a new Conda environment named MyEnv with Python version 3.9. The fifth code snippet, we're installing the TFLITE model maker. It's a library for creating a TensorFlow Lite model with ease. It's actually used for image classification, object detection, and so on. Followed by the TF-Lite model, we are installing the IP kernel. IP kernel provides an IPython kernel for the Jupyter notebooks, which is very essential and useful for this project. Then we are looking at downloading the OpenCV Python. OpenCV or open source computer vision library is a popular library for computer vision tasks such as image processing and object detection. After this, we're installing the Python package NumPy. NumPy is used for various numerical operations and so on, so it's necessary in this project. Here we are seeing the installation of the PyCoco tools. PyCoco tools is a library for working with the Common Object in Context dataset, or COCO, which is commonly used for object detection and segmentation tasks in computer vision. Here in the 10 code snippet, we are actually setting up a connection to our Google Drive in Colab and creating a symbolic link named My Drive that points to the root directory of our Google Drive for easy access to its contents. Now we are unzipping a file named iotproject.zip located in the Google Drive, which is My Drive, which contains other data for training and processing. And in this final code snippet, we're actually running the Python script located at the content train.py, and the script is used for training the model. Now let's look at the train.py file, which actually trains the model. Okay. In this file, we're actually importing the NumPy library for numerical operations, the operating system module for file and directory operations. After this, we are importing various classes and models related to export configuration and object detection from the TFLITE model maker set. Then we see that we're using the TensorFlow data and arranging the various settings in the TensorFlow library. The next part, we're actually loading the training data from the Pascal VOC format. We also see that the main classes that we are actually training a model to detect are the potholes, speed breakers, and obstructions. Next, we are specifying the model for object detection, which is the efficient TFLITE 0. This is the model that we're using to detect. This is the architecture. Sorry, this is the architecture that we're using to detect the model. After which, we are finally creating the model with the various training data, with the specified training data, the model specifications, the batch size, and other parameters. After creating the model, we're evaluating it against our validation data. Finally, the trained model is exported to the current directory with the file name test1. This is the activities that are happening in the train.py file. I hope you understood.
Sudarshan, I'm 21BI1257, and I'm going to talk about the model we have used in our project called Efficient. What is Efficient? It is a scalable and efficient object detection model that was released by Google's Brain team in November of 2019. It uses a compound scaling method that scales the resolution, depth, width for all backbones, feature networks, and box and class prediction networks at the same time. It uses a weighted bidirectional feature network for fast multi-scale feature fusion. This is the architecture for efficient net model. It has an efficient net as the backbone, and then a BiFPN layer, which then goes to the box prediction. What are its advantages? Scalability. It is highly scalable, especially when operating with limited compute data collection. It reduces the amount of data required to generalize it to a new domain. Accuracy. It has significantly higher accuracy and is very efficient across a wide spectrum of resource constraints while performing significantly less computations, making it perfect for running on a board like a Raspberry Pi, which we have used.
I'm Pratik Chaudhary, and I'll be explaining you about the model which we have created for our project to detect the potholes and the speed breakers. So the model uses two frameworks mostly, that is the TFLITE and MediaPipe. So I'll be explaining you guys about this. So let's start. So TFLITE is a framework which is used in various applications for deploying machine learning models. In our case, the TFLITE model contains a predefined object detection model that is efficient, that which we have used here. So the code which you can see on the screen utilizes the MediaPipe framework to implement real-time object detection in video streams captured from a webcam. So I'll just break down of how MediaPipe is being used in the script. So there are 7 steps basically. So the first step is the object detection model setup. The code initializes an object detection model using the MediaPipe object detector class. Second comes the video capture. Using OpenCV, the code captures live video from the webcam. The frames are adjusted to specific dimensions set by the user. Third is the image processing. Each frame captured from the webcam is first converted from BGR to RGB color space because MediaPipe's object detection models expect only RGB input. Fourth is the object detection execution. The script runs object detection on each frame asynchronously. Fifth step is handling detection results. A callback function is made which is defined to handle the detection results. Sixth is the visualization and display. After processing each frame for object detection, the script updates the display with the latest detection results. And last step is the cleanup and exit. The loop continues until the user exits the program, after which the script releases the webcam and closes all OpenCV windows. So that's it from my side. That's all about the project model which we have created. So yeah, that's all. Thank you.
Interesting, Robert. Now we'll be looking into the detect.py file of our speedbreaker pothole alert system. This is basically a script that demonstrates the real-time object detection using MediaPipe library. We'll capture video input from the camera and run inference on each frame. So initially we have the setups. We import the MediaPipe Python library, and we have OpenCV for image processing. Then we can see the run function is the main function that's going to call the model. So the arguments that we have to pass in are the model name. In our case, we are using a TFLITE object detection model, which we have retrained. And the next argument is maximum results, the maximum number of detection results. And we have this score threshold. Then we have the camera ID. We'll see the default values when we move down, where we have called the function. Apart from that, we pass in the width and the height. This part of the code starts the camera and the video is captured. Then we initialize lists to store the detection results. Then we define a callback function here named as save result, which again takes in the vision.object detection result, which is basically an instance of our object detection model. Apart from this, we have a code for computing the FPS, which is the frames per second. Then to instantiate the object detection model, we use this code. Here we initially set the base options, where we pass in the model path. Then we declare the particular options that are available, where we have set the running mode as live stream. And we have mentioned the callback function that we have defined above. Here, the detector variable is nothing but an instance of the object detection model, where we have passed in the options as an argument. And this while loop captures the frames. And using the OpenCV, which is mentioned as CV2 here, we flip the image, then we convert the format from BGR to RGB because the TFLITE model requires the RGB format. Then we call the instance that we have created for the object detection in an asynchronous fashion, where we pass in the image that we have captured frame by frame. This part of the code shows the FPS that we have calculated as an output on the screen. The detection frame is shown only if we have something in our detection frame list. That's done by this part. And this cv2.wait key ensures that the application is closed when we press the escape key. Then this is the cleanup code. Then we have the main function. Here we have used the arg parser, which is nothing but an argument parser. We have used it to pass in the arguments that I mentioned before to call the main run function, which is mentioned here. Here we have given the best.TFLITE as the model, and that's the name of a custom pre-trained model. Then we are given the default number of detection results as 5, and the score threshold as 25%, is given as 0.25. Then we give the default camera ID as 0, which is basically the default camera of the device. Then we pass in the default width and height, which is 640 and 480 here. Then we call the run function. Here we are using the args variable, which uses the argument parser. And that's it. Thank you.